want to look at this question related to properties of expectations. We're given two independent random variables. So x is a geometric random variable and y is a binomial random variable. And in the first part, we want to find expected value of x plus y. Here we're going to use the fact that expectation is a linear operator. And recall, what do we mean by linear operator? Let's just look at that. Since expectation, we're going to use the fact that expectation is a linear operator. For this, we need to recall what do we mean by linear operator. Linearity means that expectation operator can go inside summations. And what do we mean can go inside summations? We mean expectation of sum is sum of expectations can go inside summation and constant multiples can come out, right? So this is what we mean when we say expectation is a linear operator. And just to further emphasize, what does this mean? Can go inside summation. This means the expectation of sum of a sum is the sum of expectation. So since expectation is a linear operator, so we know we can write expected value of x plus y is expected value of x plus expected value y. So here we did not have to use the fact that they're independent, right? We'll use that in part B. Because expectation is a linear operator, regardless of whether x and y are independent or not, we can always write expectation of sum as sum of expectations. This has nothing to do whether they're independent or not. This is just by the fact that expectation is a linear operator. Now, since we're told that x is geometric, random variable with parameter p, so which means that its expected value is 1 by p. You know, expected value geometric random variable is 1 by time p, right? Where p is its parameter, which is probability of success. And y is binomial and it has two parameters. The number of trials is n and the probability of success is r. And we know expected value of a binomial random variable is, you can just multiply its number of trials and its probability of success. I can multiply its two parameters, right? This follows from the fact that the geometric random variable's expected value is 1 divided by its probability of success, which is its parameter. And for binomial random variable, its expected value is the product of its two parameters, which are the number of trials and its probability of success. So expected value of x plus y is just 1 by p plus nr. So in this first part, the only property that we used was that expectation is a linear operator. Because of that, expectation is sum of expectation regardless of whether x and y are independent or not. Here we do not have to use independence, right? So here we use the fact that expectation is a linear operator. This is the only thing we use, because of which we can always write expected value sum as sum of expectation. Now I want to do part B. Part B is we want to find expected value of xy, expected value product. Now here we're going to recall expectation of product is product of expectation if is product of expectation if independence holds. Now here is a condition. If independence holds. Right? So this is something that we need to keep in mind, right? So when we write expected value of sum, that's always the sum of expectation because expectation is a linear operator. But when we have an expected value for product, like expected value of xy, that is only the product of expectation. And we can only write this as expected value of x times expected value y if independence holds, and here they're given the independence. So we're going to use independence here. So here we will have to use independence, right? Since we are given x and y are independent. So just because of the fact they're independent, we can write this statement. Right? When we were writing expected value of x plus y is expected value of x plus expected value y, we did not need independence there. That follows from the fact that expectation is a linear operator. But when we have expected value of x, y, we can only write it as expected value of x times expected value y if we know they're independent. Right, since expected value of x we saw is 1 by p because it's a geometric random variable, and we saw expected value of y is nr because it's a binomial random variable, we can write expected value of xy as nr by p. Here, the key thing to remember is that expected value of x plus y will be expected value of x plus expected value y regardless of whether x and y independent or not. We did not have to use the independence assumption here. Just this follows just from the fact that expectation is a linear operator, which means it can go inside summations. But expected value of xy is only expected value of x times expected value y if they're independent. So to write the expected value of xy is expected value of x times expected value y, we need to know they're independent, otherwise we can't write this. So expectation of sum is always sum of expectation, but expectation of product is only product of expectation when independence.